Okay. Let's start with the short tazkirah, 3 minutes. Who wants to volunteer before I just call anybody? I asked you to prepare before, right? Right, for this spot tazkirah. Any volunteer? No? No volunteer. Okay, therefore I will choose. Who did last time? Was there the first time that anybody gave tazkirah in this class? No? Oh, so I mixed between the genie. Okay, never mind. So you are not prepared. It's okay. Even not prepared, you can give tazkirah, right? Because you are IIUM student. It's the National Islamic University student. So no problem lah tazkirah ni, right? Yes or no, Hannah?
Huh? I'm not sure.
Why not sure? You are Islamic University student, right?
Yes, but
Okay. Hannah, you choose one person. If you don't choose, it's you.
Ahmed.
Huh?
Ahmed.
Ahmad, you here? Okay, you have 3 minutes. What's the tazkirah?
It's been a while since I've done tazkirahs. I mean, I don't have anything. Can you give me a moment just to think of something? Or
I give you 10 seconds.
Oh no.
Huh? Maximum 1 minute. Everybody else, okay, this reminder, everybody else should prepare. I can call anybody at any time to give a tazkirah out of the blue. So, so as a international Islamic university student, you should always be prepared to become the leader for the ummah. That's why you have, so anytime people ask you to become the imam of Salah, you should say, okay, even Hannah, you go to all women prayer room, they say, Hannah, you become the imam of the Maghrib prayer, for example. So you should be prepared. So also, sometimes they will call you, okay, please give a tazkirah. Then you should be prepared. Tazkirah is just a reminder that everybody already knows maybe. But it's always good to give a reminder. Inna zikra tanfa'ul mu'minin. Allah says, verily, reminder benefits the mu'min. Have I finished my 1 minute yet? 1 second. That's what. I give you 1 second.
Okay, we can start with the Ayat Kursi.
Okay, go on. You have 3 minutes only, yeah?
Okay. الله لا إله إلا هو الحي القيوم لا تأخذه سنة ولا نوم له ما في السماوات وما في الأرض من ذا الذي يشفع عنده إلا بإذنه يعلم ما بين أيديهم وما خلفهم ولا يحيطون بشيء من علمه إلا بما شاء وسع كرسيه السماوات والأرض ولا يؤوده حفظهما وهو العلي العظيم. أصبحنا على فطرة الإسلام وكلمة الإخلاص وعلى دين نبينا محمد صلى الله عليه وسلم وعلى ملة أبينا إبراهيم حنيفا وما كان من المشركين. أصبحنا وأصبح الملك لله.
Alhamdulillah, la sharika lah, la ilaha illa huwa al-aliyyul azim. Where's your tazkirah now, Ahmad?
وكلمة الإخلاص هذه نبينا محمد صلى الله عليه وسلم وعلى ملة أبينا إبراهيم وحده. I used to say this in my high school. I think.
Oh, that was a long time ago. Okay, why have you stopped? Okay, maybe we answer that next time. But now we are waiting. Hannah is waiting for tazkirah now, brother. Come on.
Like tazkirah isn't like we just like we can just it's like reading Quran and.
No, tazkirah is like a reminder. You say something that will go to the heart of the people and make them realize something.
Oh, is it in Arabic or English?
English lah. I mean, how you think Aiman can understand what you say in Arabic?
I thought it was morning azkar. Like
No, not azkar. It's not azkar. It's something.
Oh.
It's a reminder. Reminder. It's a short reminder. It's like a reminder.
Okay, I was confused a little bit. I'm sorry. Okay.
I think so too. But I was like,
let's start over again. Okay.
Okay, you have 1 minute. Now I cut to 2 minutes only. Huh?
So okay, one reminder I would give everyone is don't think too much about the process. Just start it. Like no matter what it is that you want in life, don't think too much about it. Just start doing it, because what we always do, we always dream of having something for the longest time ever, but we never actually work for it, you know? Like we always I'm not trying to I'm not talking about money right now, materialistic things. I'm talking about like things that we want, like for us, for example, us improving developing ourselves, for example. Like if I would say if you want to improve in a certain language, you should be reading often, you should be writing often, but instead you just I wish I can, for example, Arabic. I wish I can be better in Arabic. I wish I can speak French. I wish I can speak Dutch. You're wishing, but you're not doing it, For example, if you want to go do fitness, I want to have this kind of body. I want to have this fit body. I want to be healthy. But you never go to the gym, you never work out. You just wish for it, So you just believe in the process and start doing it, and you'll just see everything falling apart. And from my experience, you just keep doing what you're doing, do what you're interested in, or do what you're passionate about. Even if you're not passionate about it, just do what you're trying to achieve, and eventually you will achieve it. Because we always procrastinate, especially social media is a big part of it. We always spend open our phone, and then we can just we'll be okay, 5 minutes, but we'll spend half an hour, 1 hour scrolling through TikTok or Instagram. And we just feel, oh my God. And you just this 1 hour you can have done a workout or read something, But instead, so I feel like one of the biggest distractions is social media. No doubt about that. So what we can do is minimize. I'm not saying completely remove it, but just minimize. For example, before you sleep, or maybe in a certain time of the day, just choose okay, this half an hour I'm gonna do, for example, Instagram, and then socialize or anything. Or you can just divide. So yeah, just avoid distraction, have a plan, and go according to the plan. And one of the best way to do that is before you sleep, have a plan of what you're gonna do tomorrow. Write it down. And in that case, you will never feel like you're free. You always feel occupied. And being occupied is not wrong. Be okay, I'm gonna play futsal, for example. This is also being occupied, Whatever it is, you're occupied. So you're not having a free time to contemplate things, right? So yeah, that's my advice for today's, and yeah, thank you.
Okay, thank you, Brother Ahmad, for the tazkirah. So I was thinking just now, start doing it. If I dream of become a queen of esport, maybe I should do it now. No, just kidding, right? So he said it must be a good thing within Sharia, the thing that Allah is pleased about. Okay. Good. So do not procrastinate, so it'd be nice if a tazkirah comes with the dalil, brothers and sisters. I already give you a reminder for next time. The tazkirah should come with dalil from the Quran or the Sunnah. So you become an ustad for 3 minutes, or ustazah for 3 minutes. So I will give the dalil to Ahmad's tazkirah. Is that Rasulullah sallallahu alaihi wasallam said, Yeah, if you have a seed in your hand and you know that the day of judgment will come very near, but you still plant the seed. You don't, so it means that you don't procrastinate. That is not part of Islam. So to stop, it's okay lah, assignment, quiz, semiconductor, very long, exam also very long, I don't have to study from now. That's not from the characteristic of a Muslim. A Muslim do not procrastinate and try to do their best in any situation. Okay, even if the day of judgment is tomorrow, and to plant the seed to get the tree, grow, will take a lot of time. But interesting, Islam, very interesting. Rasulullah Sallallahu Alaihi Wasallam still asked us to plant the seed, because planting the seed is already an act of ibadah. So you don't wait until like until a few days or few months before you do anything good. Okay, so let's continue. So from time to time, up to me whenever I want the tazkirah. Okay, so this is my class, my rule. That's if not happy, you become the lecturer. We can switch. You teach semiconductor device. Okay, right now, okay, where we are, where we stopped last time? Anybody remember? Nobody remember? Hello.
Yeah, I remember you told us to remind you to talk about the defect in multiple levels and in singular level.
Okay, let's go. Let's do that. Let me share my screen. Kenapa dia minta plugin ni? A plugin is required. Install. Weird. Previously there's no plugin. Okay. So last time, brothers and sisters, if you still remember, we talked about defects, right? And we can have generation and recombination through defects. So if it's recombination through defects, it will be the electron will recombine through the traps, and then from the trap to the valence band. And the bad thing is you don't get light coming out from recombination through traps. Now, and we only talk about one trap here. So now the question is, can we have multiple traps like this? So the trap like this. So you have many traps. Here you have 4 traps.
Madam, are they called trap or defects?
It's the same thing. Sometimes trap and defects are being used interchangeably. It's the same. Trap and defect is the same thing. So if you have an electron over here, so if it's recombination through traps here, it can happen like this. So go there, go there, go there, go there, go here, right? Possible. It's possible. Okay. So you will go through multiple traps. So if it's generation, okay, go here, go here, go here, go here, go there, right? So it's even easier if you have multiple traps like this, because the energy level, energy that is needed to go from one trap to another trap is now divided by 1, 2, 3, 4, 5 by 5 levels. So if it's 1, if this 1 EV, 1 divided by 5, how is what? 1 divided by 5.
20, 0.2.
20, 1 divided by
0.2, sorry.
0.5. 0.2. So 0.2 is very little compared to last time. We need to have 0.5. Okay, now this is multiple trap. Now, so multiple traps and multiple levels. So it can also be like this. Macam-macam. We can have it. It can be like this. So Amirul, why you come late?
Yesterday I couldn't come here because there's conference.
Sorry?
There is conference yesterday, so I couldn't come to your class.
No,
Because
today,
today
this morning. This morning you come late. Why?
Oh, I'm from toilet.
So next time please come early. Otherwise I will not allow you in. Okay. This applies to all my students. So our class start at 8:30. All right. So now let's see here. So you can have also the trap like this. Same level, but many. Is the same energy level, but it's many like this. So therefore, if you're going to have a recombination or generation, it has to be like this. Okay, something like that. All right. So you can have all these kind of traps. Now, next question is, if I've asked you a question. Okay, you can see the relative difference, right? So I call this ET1, ET2, ET3. So between these three traps, which one is most active? Tell me. I give you 1 minute to think. Okay, 30 seconds. 1 minute too long. 30 seconds to think within these three traps. Which one is most active? Already have to answer.
I think 82.
Okay, Ahmad said 82. Others?
83.
Who answered 83? You say your name and then say your answer. Huh? Rahimi say what?
83.
Okay, Rahimi 83. We still have like, you know, different answer, a difference of opinion. Khilaf. This is not khilaf. This is like wrong. Khilaf is like small thing. So this is like it's either right or wrong. Okay. Who else? So,
82, Amirul.
Amirul 82. Who else?
81, Aiman.
Aiman 81. The rest? And make sure you have an answer why. Yeah, why just in case you choose that one. Who else?
81 Faris.
Faris 81. Okay, who else?
Elmi 81.
Aimi 81. Who else?
Hassan
81.
Hana 80. Siapa tadi? Kamalia? Siapa yang jawab tadi? You need to say your name.
Maisara 81.
Maisara 81. Who else?
Hassan
Saya
81.
Hassan 81. Okay, who else?
Kamalia 81.
Kamalia 81. Who else?
Hana 81.
Hana 81. Anybody else not answered yet?
Ikram 83.
Islam 80.
Ikram 83.
Ikram 83. Who else? Not answered yet? Anybody who I didn't mention the name yet?
Islam 82.
Islam ET2. Okay. Now let's ask Ikram, why ET3?
I think because it is near to conduction band.
Huh?
Because it is near to conduction band.
Near to the connection band. Okay. So what if it's near to the connection band?
So yes, more energy.
Apa?
Yes, more energy.
What has more energy?
The track.
The truck has more energy. So why is it more active?
I'm not
Okay.
so sure that.
I'm not sure. ET2, Islam, why ET2?
Because it's near from the main gap for there. The electron will be
Can you speak louder? I always have problem with you. Cannot hear.
because the thread is near from the main gap there, so the electron can jump to it easily. So it will be more active.
Hannah, can you hear what Islam was saying?
No.
Okay, Islam, you need to say until Hannah understand what you say.
Are you hearing me?
Hannah.
Yeah.
So repeat your answer again. Islam, we are waiting.
You hear me, madam?
The same, it's the same like before.
Give me 1 second.
Okay, while waiting for 1 second, let's hear from Ahmad. Why ET2? You said ET2, right, just now?
Oh, yes, I said. First of all, it's closer to the valence band.
Mm-hmm.
It requires less energy, so it can jump. So and it's also it just for me it seems logical that it's since it's closer to the valence band, more electrons there are, are wanting to jump, and the ET2 is the closest thing there. So for me, like from my point of view, I feel like ET2 is the one.
You feel in
I mean,
engineering,
based on my observation, ET2 is the active one. I could be wrong though.
Okay, let's hear from who answered ET1. Allah Akbar, what's wrong with my today? Okay. Siapa ni? Who answered ET1 just now? Let's call Kamalia. Why ET1?
I just say T1 because it has the same energy. It is in the middle, right? So it has the same energy band gap. So
Energy band gap is this one. There's only one energy band gap. This one.
no, energy, the one we divide by 2. What is it called?
It's just energy.
Yeah, the energy is the same for hole and electron. So it has the most active one, I think. And for E2 and E3, the energy is not the same. So it doesn't.
But this is very small.
But for hole, it's very big for who to be excited.
So let's talk about electron only. Then how?
If it's only
If it's electron only, then ET2
then
will be
it will
the
be
active.
ET2 will be active.
Awak ni kelakar juga. Okay, alright. Who agree with Kamalia? The one who answered ET1. Do you agree with Kamalia or no? Hannah. Okay, you answer ET1.
ET1.
Do you agree with Kamalia's answer?
I think if we were talking about electrons only, it would still be ET1
Why?
because the distance is the energy is equal. It's not like small and then large.
So,
So I think if it was ET2, it would have a higher chance to recombine. So because of the larger energy.
say again, Islam, listen carefully and tell whether you understand what Hannah is saying. Okay. If you understand, I will ask you to repeat what you understand. Okay, go again, Hannah.
I think that if we were to talk only about electrons, it will still be ET1 because the energy levels is equal. If it was ET2, then I think it would jump to ET2, but then I'm not sure if it will go to the electron, the conduction band, because the gap is too large.
Okay, do you understand Islam? Huh? Answer me.
Yes, yes.
Okay, what do you understand?
She said that the 81 and 82, the 82 will be near the balance gap so that electron can jump. But after that, the gap is more wider so that electron can jump with this energy, with the energy that have.
So do you want to change your answer or your answer is still ET2?
I think 82.
Your answer is still ET2? Why?
So the question is, which one is more active?
Oh yeah,
which
most
one is-
active. Which trap level or which trap is most active?
Most active means like there's like electrons go and give energy and
Most active means it's the
energy.
one that more recombination and generation will occur.
Oh.
So yeah, Islam answer. You need to think faster. Okay, give you 1 minute to think. Amirul, what's your answer?
I think I would change the to ET1 because by active more recombination, then ET1 would be would have more recombination due to the
If
equal
generation, okay, let's say scrap the recombination. So if it's electron, most active generation, which one?
most active generation, which one? Kalau nak ET2 lah sebab less energy required.
Okay, so macam Kamalia tadi lah. Okay, you know, Islam, back to you. Come on.
I think it is 81, not sure. Because you said that it will be like recombination and generation. So for the generation, 82 for recombination, I think 81 and 81 can more active in both.
Okay, everybody.
I want to say something.
Okay, sure.
Okay, let's think about this. So we say that the electrons will jump from the nearest to the nearest band, to the nearest trap, right? To the nearest one because less energy. So if it jumps from ET2, I mean, Hannah said the ET1 gap is somehow in between the valence band and the conduction band, right? But can it just jump from ET1 to, from ET2 to ET1 and then
No. This is separate cases. So one case only.
Oh. Oh, I thought they're all together.
No.
Yes, the
Otherwise, my
ET1.
question will not be valid. Why would I ask which track will be the most active?
Okay, now now it's clear in my head. And then I'll choose ET1 then. Yeah, it makes more sense to choose ET1.
Okay, now we have people changing their minds. So okay, so I will tell you the answer now. I think otherwise will be like the whole class discussing about this. Okay. So there are 3 cases here, ET1, ET2, ET3. And which one is the most active? Here, remember when we talk about generation recombination, I kept on saying about the word, what you call it, probability. I explained before why we talk about probability, because electron can behave like a wave. Therefore, we cannot pinpoint where electron will be at one time. So it's just a probability that electron will be there. Okay, we cannot be sure that electron will go anywhere. It's just a probability because it's a wave. It can sometimes be here, sometimes be there. So that's why we say it's probability. Now, so for example, E2. So if to debunk Kamalia's answer, so for example, E2, if we do generation, right? E2 say this go here, okay, very good. If this is 1 EV, this is maybe 0.01 EV. So it's only required 0.1 EV. But for when I say active, it means that it means you need to have free carriers or you lose carriers, right? Generation recombination, that's the definition. Therefore, this electron cannot just stop there. You need to go all the way here, right? Therefore this apa nama ni? How do I make it better? So this, so if this is state 0.1, this 0.0 0.1 because 0.01 0.1. So 0.1 EV, this will be 0.9 EV, right? So still this electron here need to find 0.9 EV. The probability of getting a 0.9 EV is very small. So as I mentioned before, it's the same as concept discussed before here, you know. So, but okay, the same goes here. The same goes here. Okay, now it's difficult for us to jump. Maybe here you need 0.7 EV. Here you need 0.3 EV. So although it's easier to go here, but to go from here to here, you need still 0.7 EV. So the total for an electron to go across the band, still a lot. 0.7 is a lot more. Okay, so it's the same. Recombination also the same. The recombination also here easy jump and then more difficult. Here difficult then easy. However, if it's ET1, so the answer is ET1. ET1. So for generation, here we'll take 0.5 EV, and the same will also get 0.5 EV. So the number to get 0.5 is easier than to get 0.9 and 0.7. Therefore, the most active, always the most active trap is in the middle of the band gap. Whenever you have a trap and the characteristic of the trap is in the middle of the band gap, it's always the most active. So you would like a trap to be like this. Although you have many of these traps, for example, but it will be less active or like this. If you have in the middle, and although you don't have many, but you'll be very active. So because it's easier, probability for electron to go there is more probable. Okay, any question? No? Okay, make sure you understand. In in the quiz or in your final exam, I will ask questions. I will twist the question to check your understanding. Okay. Now, okay, kat mana? Where should we go next? Anybody knows? Anything that I haven't covered? Aiman? The thing that I asked you to find out. Anything that I haven't covered yet? Huh?
Madam,
Yes.
yang graph band gap versus lattice constant.
Okay. All right. So let's see. I will now share my listen. Slide one. Okay. Share my screen. Okay, this one, right? Okay, so now you understand, you already understand lattice constant. We covered this in the class, so it's lattice constant. You understand what is the band gap. So this is a graph plotting the band gap versus lattice constant for different semiconductor material. Okay, so gallium phosphide, aluminum phosphide, gallium arsenide. It can be gallium arsenide phosphide, no, tapi it's not here. So not all of the semiconductors are materials are here. So you will see that some of the apa nama ni, and they color coded this. Kenapa ada yellow ni? So the red are the from the group 4, silicon germanium, silicon carbide, 3,5. You can have a semiconductor from the group of 3,5. So 3,5 is, for example, is gallium arsenide, indium phosphide, aluminum nitride, and then you can have from group 2,4, aluminum nitride, and this is zinc oxide. Okay, so these are different types of semiconductor material. So what does this telling you? Okay, number one is you can see the band gap. So let's say I ask you to design a detector, semiconductor photo detector, or I ask you to design a laser or LED. So depending on the wavelength, so you need to find the wavelength that is suitable for the application. For example, you want to make, I ask you to make a red LED. Okay, I ask you to design a red LED. So which material will you use? So the one that, if you can see the the colors here. So these are this band gap shows you the energy that when recombination occurs, that will release that kind of energy. Remember, when we talk about direct band gap material, if you have recombination, it will release photon, and the photon can be visible or non-visible. The photon, the light, can be visible to our eyes and will not. The electromagnetic spectrum, the light spectrum, you have visible spectrum that your eyes can see. Also, the light can be beyond the visible light. For example, infrared. Infrared, our eyes cannot see, but the semiconductor can detect it. Okay, because of the band gap. So the band gap that gives out visible light is here. So they color it for you from this. So from the smaller energy to a larger energy. Smaller energy means longer wavelength. So go and find out, go Google, that's very easy. The relationship between energy and wavelength. Okay, I will not teach you. It might come in the quiz or exam. So go and find out. So I can just say I told you in the class because but you are too lazy to find out. Then it's your problem. It's easy. It's a relationship. Find a relationship between energy and wavelength. So the higher the smaller the energy, the longer the wavelength. So the longer the wavelength is more reddish. The higher the energy, meaning the band gap is bigger, it means it's more towards the blue purple. Okay, our eyes can see up only to purple. After that, it go to ultraviolet. Ultraviolet, our eyes cannot see anymore, right? So but the semiconductor can gives out these colors. It can gives out up to from red to infrared over here, or from purple or violet to ultraviolet over here. Okay, so depending on what application, you need to know what application that I ask you to find. Then you need to identify what kind of wavelength, what is the wavelength required. Therefore, you convert into energy, electron volt. Make sure you know how to convert from wavelength to energy and EV, because not joules. Okay, in semiconductor, when we talk about energy, we don't talk about joules, because joules are too big, the numbers. So it's electron volt. So my second reminder, go and find out how to convert. It's very easy, and your final exam will be open book, no problem. But make sure you know where to find the information to convert from what do you call it, joule energy to electron volt. Okay, your quizzes, maybe one quiz will be open book, two quizzes will be closed book. Okay, so when you close book, you cannot open anything, but your final exam will be open book. Okay, then where was I? Okay, so this is the wavelength. If recombination, it will give us this color. However, silicon carbide here, although it falls within this this band gap, silicon carbide is not a direct band gap material. Silicon carbide, so not all of the material here are direct band gap material. How do you know? You need to Google and find the information in journal or textbook. Okay, you need to know which material are actually the direct and which one are not direct. Sometimes you can find a list of all the direct and indirect band gap material. Okay, so number one, the most important thing is the band gap here. So you choose, for example, I told you just now, find apa namanya, I asked you to design a red LED. So maybe you want to use gallium phosphide. It gives like something reddish, right? You want to use gallium phosphide as the material. Okay, now, so that's on which material. Now, why do we have this lattice constant over here? Okay, what is lattice constant? Elmi. Every morning I have this sinus, so every early morning I will be like this, huh? Yes, Elmi.
Lattice constants is the distance between atoms of the material or the semiconductor material.
Okay, good. So why is lattice constant over here? Now, in order to answer that, I will talk about homojunction and heterojunction now. Homo structures, bulk, and hetero structures. Okay, let me draw. Okay. Now let's talk about maximum is only 10 pages. Okay, never mind. So Okay. Bulk, sometimes we call it bulk semiconductor. So bulk means this ketul lah, just one piece. For example, if I buy a if this a piece of gallium arsenide semiconductor, the whole thing here is a gallium arsenide semiconductor. This is a bulk semiconductor. Just everything are from gallium arsenide. The whole thing is a gallium arsenide. Maybe I can also buy a bulk silicon. Okay, Si. This is gallium arsenide, GaAs. This is silicon. Also, I can buy a bulk silicon. The whole piece is actually silicon. Now, so bulk means everything that we talked before. Okay, everything that I teach you in the class before are all bulk. We didn't mention about hetero structure yet. So the easiest is bulk. It's a bulk. You can buy a LED of gallium arsenide LED. When you say gallium arsenide LED, it's a bulk using bulk gallium arsenide semiconductor. But what is heterostructure and why do we need it? Okay, now let's say why do we need it? That's a good question. So, for example, I want to make a. If I put, is it possible if I want to have, okay, this is my gallium arsenide piece of semiconductor, and I want to combine it, put into one device or into one device. Indium arsenide. So in order for me to make one, so this become one device. I want to make a device now. So now we're going towards device, semiconductor device. Previously it's just all material. So now, is it possible to make something like this, to put together gallium arsenide and another material, maybe indium arsenide? What do you think?
Can, madam.
Why? Why you say can?
Because
Yes.
because different material. Wait, no.
Wait. Okay. Yes. Still waiting. Jangan bagi saya berjanggut dah. Aiman, possible
because,
yes, Rahimi, because?
I don't know, but it can. It hetero
Maybe it's
structure,
magic.
right?
Heterostructure. Is it magic? You think?
No, because it have different, what we call? Different material and have different band gap and lattice constant.
Okay, let's make this more interesting. I want to put this gallium arsenide and I want to put silicon. Possible or not possible in one device? Possible. Who say? So, okay. Hana, Faris, kita tak dengar soal Faris lagi pagi ni. Faris, what do you think?
Not sure, madam.
Huh?
I'm not sure.
You're not here lah, brother.
Not sure.
What are you not sure?
Whether it can possible to have
Pick a guess. I don't care, madam. Why should I care? It's very important. Heterostructure is in everything, most of everything that you have nowadays. Who wants to answer this? Anybody wants to answer this? Faris, choose one person. Because you cannot answer, right? You find one person to help you.
Hassan maybe.
Hassan? Okay, Hassan, please answer.
I think it is possible to create a
Why?
difference with these
How?
two semiconductors. How? I'm not sure, but I'm just guessing.
Why are you guessing it's possible?
Because I think I've seen somewhere that a complex device is created with more than two semiconductors like this.
All right, thank you.
I'm not sure of the reason.
Huh?
I'm not sure about the reason.
Okay. All right, brothers and sisters. So this is where lattice constant becomes the hero, becomes important. Now, what before this we discuss it's possible or not possible. Why do you want to do this? Any guess? Why do you want to put different material in one device?
Want to improve?
Yes, Rahimi?
Want to improve?
Tak
Just like
dengar lah. Huh?
want to improve. Just like doping.
Okay, what do you mean improve in what sense?
Just like one material have one advantage and another one have one advantage. If we combine, we get two advantage. Can you hear me, madam?
Yes, I can hear you.
Ah.
Okay. So let's do, for example, gallium arsenide and indium arsenide. Gallium arsenide, the band gap is 1.4. Indium arsenide, the band gap is 0.7 eV. I give you 2 minutes, everybody, to draw the energy band diagram of this structure. Draw me 1 minute pun enough lah. 1 minute to draw me this energy band structure and show it to everybody. Finish that 1 minute. 1 minute. Nobody asked me, assume it's intrinsic. Both are intrinsic. Since nobody asked me lah, I was hoping you asked me, is n-type, p-type, because, right, but it's okay. I tell you, it's intrinsic. Because make it easy first. After this, make it more interesting, more difficult. Okay, finish. If can you show us your drawing? Afridul Ifaj. Yeah, let me stop sharing. See, show it. No. Okay, interesting. So that show both material, but it's not combined. But even still wrong. Can you show it again? Aiman, is this correct or wrong? And why? Aiman, Kamaru Zaman.
Ifash. Can you
Huh?
share again the picture? Wrong.
Why?
Because the material does not combine in.
Is that the only thing which is wrong?
Can you share again?
Everybody else watch carefully. Is that all, Aiman?
He doesn't label.
Okay, what else? Dia ada dosa besar kat situ. This is big sin. This the one you tell you found one big sin. There's another big sin.
Band gap
band
level
Okay,
gap
to
kan?
big
energy
sin
looks
when you
the
are jahil,
same.
you don't know. So we are learning. It's okay, Faj. But at least when you make this error, so that everybody else knows it's not right. So what's the other thing which is wrong?
The band gap level, it looks the same. There's no change in it. Even though he labeled it, there's no change in the drawing.
Do you understand, Faj?
I drew it.
Yes,
Can you
but I
see?
didn't do that because I'm putting a value already. That's why I didn't show the.
You can't see my drawing. It's blurry.
Yeah, your drawing is like cannot see. So
I'll take a picture.
so actually it's wrong to draw like that. You need to show the relative difference. If you draw in the quiz or exam like that, but in the quiz normally I will put note show the relative difference. If you do that, if I put that, whether I put it or you don't put it, you should know when you draw, you need to show the difference between 1.4 and 0.7. 0.7 is half 1.4, right?
Yeah.
EV. So one should be big, one should be small. So that's one problem. Another two problem is this is when you draw is two separate material. Now you should be combined. The band gap should combine. So anybody want to show their drawing, which we all can see?
Madam, can I show in the Telegram group?
Yes. If you cannot show it here, you can put in the Telegram.
I don't know if this is right, though I might have mislabels.
Okay, you can put in the Telegram. While waiting, maybe my Sarah, you can show, can we see your drawing through your camera here?
I put on Telegram too.
Telegram lah, okay. So where's your Telegram? Tak ada pun? Okay. So everybody seen Hannah in Telegram. So, okay. Good. So Hannah's drawing is right. So you will see that. Okay, now let's spice it a bit. Okay. There's nothing fun. I know as a semiconductor lecturer, this is fun for me. Okay, let's make this exercise a bit to add more spice to it. So I want you to draw that. Now this, I want you to draw this. So what Hannah was drawing is right. So you can check Hannah's drawing and compare with yours. Now I'm drawing this. Okay, can you draw that? Okay, 3. Now. Okay, give you 1 minute only to draw. 30 seconds pun can draw now. Okay. Finish drawing. You can put in Telegram your drawing. Everybody snap a photo of your drawing, put in Telegram. Alright. Quickly. what Hannah draw before is correct, but not totally correct. I will tell you why later. So I will draw for you the right one after this. And it shows how, you know, semiconductor is not that straightforward. Anybody, come on, draw me, put me Telegram, huh? Okay, one person. Who's this? Ahmad. Okay, Ahmad draw one. Okay, good, Ahmad. So Ahmad similar to Hannah before. Where's everybody else drawing? Kamalia, Elmi, Amirul, where's your drawing? Hassan, Islam. Okay. Hassan is there. Who is K? Okay, apa? Kamalia. Okay. Okay, this is, who is this? Aiman. Aiman shape is a bit different. Okay, Aiman, you can have a discussion on the macam-macam jawapan lah. Okay, so you have, you don't have name here, Amirul. Okay. Who is I? I is Ifaj. Islam, where's your drawing? Islam, oh Islam. Can you hear me? My Sarah with the cat hugging. Islam, where are you? Okay, all right. So, okay, brothers and sisters. So your drawing, as I mentioned, Hannah drawing like this before. Rahimi pun lambat Rahimi ni, nak betul. Laju sikit, okay. Now, brothers and sisters. So what Hannah, the I said correct, drew like this before. So dia macam ni. Okay, so let's make it simple first. We just drew this part first. Okay, so this is what Hannah draw. Okay, this is 1.1, 1.4 EV. This is 0.7 EV. Connection band. Normally we put at the end. Connection band, balance band. But the actuality, how does it look like? This band gap when we draw, it looks like this. It looks like this. 1.4 EV, 0.7 EV. Okay, so in actual, when we are drawing the energy band gap, if it's put, we call this heterostructure, it will look like this. Okay, now is this wrong? Okay, in this one, I'm not covering in this course specifically, but apa nama ni, if you go in detail, let's say if you want to do a master or PhD, this definitely you need to know. When you have a heterostructure, you have different types. You can go and Google type 1, type 2, type 3. So depending, how do we know in the end the band alignment, the name where we call this bila kita cantumkan dia, when we put them together, we call this band alignment.
Madam.
Huh?
Yes. That's why we call it what, bulking.
Apa?
Right. Just what? Like bulking process. No.
I never heard of bulking process.
Bulk semiconductor.
No, this is not.
Oh.
This
This
is
hetero.
this is all hetero.
Okay,
I
okay, okay.
finished with the bulk. This is all hetero.
Okay, okay.
This is all hetero. Hetero means more than one material in the device or in the structure. Heterostructure means more than one material per structure or per device. So here it's very clear, right? You have two materials over here. Two materials over here. So it's a heterostructure. But the thing is, how you draw it? You draw it like this or you draw like this. It depends on the band alignment. How do you know? You have to, you cannot guess. This one is the same as the direct or indirect band gap material. You need to find out from journal. People have done research. Then they, from their experiment, they know that it's actually the band alignment like this or like this. But generally, most of semiconductor device like this. Okay, it's like that. Okay, this one ada tapi rare. Betul dia ada satu lagi type yang pelik sikit. I can't remember. So there are 3 types. So you can Google it. Band alignment semiconductor type 1, type 2, type 3. Okay. So, but let's say in the exam you draw like this. I don't give fully wrong lah. But it shows that you are not. You don't do enough homework to know it's like this. If it's in the what do you call it, final exam. Okay, it will look like this. Now, so this is for just get. So this is let's focus on this. So this is gallium arsenide and this indium arsenide. So where's the now if you want to do like this, we add another part of this and then it's sandwiched by another gallium arsenide. So it will look like this. Okay. So this is just the band gap of the structure. So you have, so what we call this structure, we call it sandwich. Macam sandwich you eat. So you have the interior, the filling is indium arsenide and then the bread is gallium arsenide. So you say this is a sandwich heterostructure between gallium arsenide and indium arsenide. So now it is possible. We can draw the band diagram like this. Now the question is, why do you want to do this? Why? There's a brother said going to improve. So what are we improving? Why are we complicating our life? Anybody? Because we engineers, we like to complicate life. No, we engineers, we always want to simplify things. Anything's complicated, we try as much as possible to simplify. That's our philosophy as an engineer. So why do we have this? Anybody?
Is it because we want to control the semiconductor?
Yes. So what kind of control?
The conductivity and.
But conductivity, okay. But if you put like this, does it improve the conductivity? It makes more complicated. Electronic to travel here. Yes. Who's that?
Ayman.
Ayman.
I think that it relate to band gap and lattice constant. We want to make a new band gap energy. Relate
Repeat.
to the
Repeat.
Oh, I think that we want to introduce new band gap energy.
Why?
Because as in the graph before, right? There's a material that at 3, at 4, at 5, and at 3. So we want to introduce the 4.5 material. So we heterostructure the material.
But it doesn't matter here. Here still the band gap is 1.4, 0.7, and 1.4. It doesn't change. Okay, Amirul, you answer this. If you don't know this, then you'll be in trouble. You cannot continue your study.
We can the band gap energy, the let's
Yes, okay, we cannot hear you. Why do we need this structure? Why are we complicating our life?
We can have like 2 level of bandgap energy.
So what?
For 1.4 and 0.7.
Yeah, of
so we
course.
have
Why,
two condition.
brother? Why?
Why? Uh, energy, energy efficiency.
Explain.
We can have it work at 2 condition. First at 1.4 and second at 0.7. So it's like
okay, I was hoping you
different
answer something
work.
else, but yes. So one of the reason is so in one material, if you have a material like structure like this, right? You can have the combination of two energy. So you can have if the electron recombine like here, you will release 1.4 eV of light. Gallium arsenide and indium arsenide both are gallium arsenide is a indium arsenide, and I'm not sure whether indium arsenide is also a direct bandgap material. Gallium arsenide, indium arsenide both direct bandgap. So you can get energy coming out of 1.4, and then if you have recombination over here, you get 0.7 eV. In one device, you can have two colors, right? Sometimes, do you want to buy I don't know, let me give an example. The 3-in-1. If I say, oh brother, buy this device, 3-in-1, and then another seller buy with 10-in-1 thing, right? So of course you want 10-in-1 in one device, right? It can do many things. It can brush your teeth, it can clean your house, it can wash your car. So similarly, when we have this kind of structure, if you see here recombination, you can have recombination of the light coming out can be two different wavelength. That's one. What else? Why do you want this? Amirul, you're supposed to answer still. Yang lagi penting yang patut kena mengena dengan awak punya project lah.
Sorry, apa tadi?
Why do we need this heterostructure? Other reason?
Kalau if based on graph lattice constant, we can have like 2 different visible light macam tu.
No, we already talked about that. That's why I just say just now, Amirul. Saya dah sebut. What else?
What else?
And this is very important to your project. You don't know?
Energy bandgap. Apa lagi yang ni?
Okay, never mind. Amirul, my suggestion to you, go and get the book of Light Emitting Diode by Schubert. Make sure you read the book.
Light Emitting Diode by?
Schubert. Aiman, you have the book, right, Aiman? Aiman, my FYP. So he's reading the book.
Yes.
You can put in the Telegram the name of the book. So Amirul, is vital for you to know all this. Okay, read.
I put the name of the book or put the PDF book.
Just put the name. Let him find the PDF himself.
All right.
Nothing comes easy in life. Okay, so put the name and PDF, and by next class khatam the book, Amirul.
By next class khatam the book.
Yes.
It's textbook.
It's a textbook. Yes.
I will try, inshallah.
You don't have anything else to do in your life right now. Yeah, so you can khatam the book. Okay, now. So another thing, brothers and sisters, which is important why we need heterostructure. Number one is we can get recombination or generation of different wavelengths. And this is important for both devices that require recombination and generation. For example, solar cell require generation. Photodetector also require generation. Later on, I will talk about what is photodetector, what is solar cell, and LED and laser. The more important is the recombination. Also, we can have production of, I said, different wavelength. Another thing is you can have when you talk about efficiency of a LED or laser, what happens is if you have a electron over here, the electron can what's the word? In Malay, we say berkumpul. In English, we say accumulate. The carriers can be accumulated here. The electrons can be accumulated. The free electron can accumulate here. The free electron, a hole will be accumulated here. Therefore, you increase the probability of recombination. Because if you still remember, when we have an electron, when we have free electrons over here, when you have free electrons at the conduction band and free hole at this valence band, it will move everywhere. It will just go everywhere. So sometimes it will combine here, sometimes it will recombine here. But when you make normally when you make a LED or laser, you only want one color to come out. You only want one color and you want it to be efficient. You need the probability for recombination to increase. Therefore, by having this kind of well, it's not well, it's like macam this electron will move, and then when the electrons come here, it will be trapped in here. It can go out, but the probability of going out, you need to overcome this energy. But it means that most of it come here, and the whole also move around and come there, and therefore you have recombination here. So it will increase the recombination efficiency. So as an engineer, if you understand this, that's why LED laser, most of it are using heterostructure. If you buy LED, mostly heterostructure, number one. Number two, later we'll talk about quantum well and quantum dot. Okay, quantum well and quantum dot are just this heterostructure here. It's just a heterostructure, but it's smaller in terms of size. That's all. It's not very complicated, but the physics behind it is complicated. We give to physics people lah. So next class, Amirul will tell us about quantum well and quantum dot, Amirul. Because we are fortunate to have a physics people. We are not physics. I'm not a physicist. I'm an engineer. So we ask the physicists lah to explain to us. Okay, if you don't understand, you ask your supervisor, and then you can explain the class next class, Amirul. Boleh? Okay.
I will try.
Alright. Make sure not ajaran sesat. Okay. Now, okay, brothers and sisters, that's why we need, when we do this heterostructure, okay, when we do 950 dah, when we do heterostructure, when we want to put two materials together, it's very important to look at the lattice constant. Okay, that's why we go back to the lattice constant. Why? I will do this very fast, although the time is up. So for example, this is our lattice before. So let's say this is gallium arsenide. Okay, this saya tembak je. I'm just like estimating. It might be wrong. The lattice constant. I'm just to show you the number is not accurate. Let's say this is 5 Armstrong. Okay, and then you have the indium arsenide. So if the indium arsenide lattice constant is, for example, 4.5 Armstrong, so it will be like this. Okay. Okay, these are the two materials, but you want to put it together, so it need to bond. Okay, the bond of each one need to bond. So for example, this let me get the yellow. So this is covalently bond with each other in one material, gallium arsenide. This also like covalently bond with their atom in there. So now we need to bond between the gallium arsenide and indium arsenide. Therefore, dia jadi macam ni. So it becomes, this will bond with this will bond with this will bond with this will bond like this. So you can see the bond is stretched. So this what we call it stress or strain inside a semiconductor. And this bond, so the bigger, can you imagine, this is, for example, this is 4.5 Armstrong. So but the way I draw it is a bit exaggerating lah. But if you can imagine, if this is 5 and this is 10, then it will not be able to bond. So there will be a lot of defects. So here you can have the bond, but the bond is strained. But when the when the lattice constant is very different, you cannot even put the two together. It will fall apart. It will not bond. Therefore, you don't get a heterostructure. So looking back at our graph that I talked before, the graph in the, the band gap with lattice constant is important because you want to find material that have, they call it lattice matching. Lattice match, MATCH. So when the lattice match, then it become a good bond, therefore you get a good heterostructure, therefore you get a good device. So the graph is extremely important. So when you design something, number one, you need to know the band gap. Number two, you need to know whether if you put a heterostructure, how about the lattice mismatch? Is it lattice match or mismatch? Mismatch meaning it doesn't match. Therefore, you cannot make a bond. Therefore, you have a lot of defects. Therefore, the device will have problem. Okay, so that's the importance of that graph. It's extremely important. So go and study more. If you don't understand, ask me next class. Okay, let's end the class today. If you have any question, keep it, write it down. We'll discuss next class. You need to tell me I have a question. If you don't tell me, then I will not answer lah. Okay, can we have a brother to recite the dua? Sorry, 9:55. Whose turn is it today? Those who have not recited dua, it's your turn now.
Ma'am, I'm going to recite today, inshallah.
Okay, Hassan, go on.
Allahumma amin. Rabbana la tuzigh qulubana ba'da iz hadaitana wa hab lana min ladunka rahma innaka antal wahhab. Allahumma jaddidil imana fi qulubina. Ilaha illallah wahdahu la sharika lahu lahul mulku wa lahul hamdu wa huwa ala kulli shay'in qadir.
Okay, thank you, Brother Hassan. Let's end with Tasbih Kifara and Suratul Asr. Subhanakallahumma wa bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilayk. Bismillahirrahmanirrahim. Wal 'asr innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Thank you.
Thank you.
Assalamualaikum.